Now, we talked when we were doing cylinders, and we talked back when we were doing point charges, that your electric field is sort of a sum of the individual electric fields due to the individual charge distributions. I keep getting these weird when I go to connect a line. And so if I have two slabs and I could figure out the electric field due to each slab, then the vector sum gives me the whole thing. So I'm going to start by talking about two slabs of charge that are separated by some distance. And I'm going to make this one E1 and this one E2, or should I say slab 1 and slab 2. If they're positive charges, we know that the E field points away. And my slab 1 would have arrows etc. And I'm going to use different colors for these, I think. And my slab 2 will have electric fields pointed away from slab 2. So my net electric field in different regions let's just do it this way. So above both of them, we can think of it as having E1 and E2 both pointed up. Both in the positive I-hat direction. If I am in between both of them, then my E1 was pointed down, but my E2 was pointed up. So I'm going to have minus E1 I-hat plus E2 I-hat. And below both of them, they're both pointed down. last one should have been. The other color. And so I can find, if I know the equivalent surface charge densities of both of those, I can find the E field. Which leads us into the last case I want to talk about here, a non-symmetric slab. And by that, what I mean here is that I'm going to have symmetry in X and Y, but not symmetric in Z. It turns out that the way we can think about this is that the E field at any particular position in Z is going to be the E field from below Z minus the E field from above Z. Which is really kind of what we have here when we're looking about this, because this is the stuff below and this is the stuff above. So it's the E field from the below minus the E field from the above. In terms of an integral, I'm going to show you here, because they formatted all the equations for me nicely here, that we can actually write Gauss's law in a differential form where I've got some amount of charge well, I've got sort of the incremental electric field contribution as a function of Z, but this could be rewritten out in terms of everything below from infinity up to minus infinity up to Z, and then from Z up to positive infinity, as the way we can find our electric field at any space. Now, I'm going to break this down just a little bit into some other cases. just again so we can think about our three regions. And so I'm going to grab this thing and copy it and paste it down here. If you're below the slab, so let's just say our slab goes from some Z1 to some Z2. Let me write this out a little bit easier. Then you've got some density function in that range, and rho is equal to 0 outside that range. So if you're below Z1, then you've got an integral there's no charge underneath Z. And here, it actually only goes from Z1 to Z2, rho Z dz. And here they're using Z prime as the integration variable just to make it a little easier to see what's happening here. Because above Z2, there's also no charge density. So I don't have to go all the way out to infinity. I just only have to go up. And I don't really have to consider the stuff below, because all of that's going to be 0. And so my E field is going to have a minus the integral of, well, there's going to be a 1 over 2 pi epsilon naught Z1 to Z2 of rho Z prime dz. And from our previous discussion, I can think about this as being the equivalent surface charge density. Above Z2, I'm going to have 1 over 2 epsilon naught. The integral on this side, I don't have to go all the way down to minus infinity. I'm just going to have Z1 to Z2. And the minus for the stuff above it is there's nothing above it. And so it's going to become plus 1 over 2 epsilon naught. So outside of this slab, even though it's not uniform, the field is that sigma, well, let me use my other sigma just so we don't confuse ourselves, but know that other books It doesn't matter that it's not uniform inside the slab. It is uniform outside of the slab.
Oh, them both Z1 to Z1?
Z1 to Z2. Trying to write these small subscripts. Now, what I'm going to go through and in a different video is I'm going to do an example with a specific non-uniform distribution and calculate it both outside and inside so we can find the example for any z value. And so I'll actually do that one with a specific density function and then actually with some numbers as another example. Okay? So we'll leave that for another video time-wise in terms of class.